Okay, so the next lesson will be on the golden ratio. So, the first thing we'll talk about, well, what is the golden ratio? Well, the golden ratio is approximately about 1.618, and it's basically like pi. It's a non-repeating, non-terminating number. I actually have the derivation on the next two slides, but I really don't want to focus on that. I'm not really that concerned about where the number comes from. It does come from an algebraic concept and equations, but we're going to just focus on basically the value of 1.62 as the golden ratio. And often in art and in things like interior design or architecture, the golden ratio is thought of as a ratio that's aesthetically pleasing to the eye. So pleasing to the eye. And again, I'm going to skip the derivation. So basically with the golden ratio, the first concept that comes out of that is what is called a golden rectangle. Now, a golden rectangle, again, the idea is if you divide the length of the rectangle by the width of the rectangle, you will get the golden ratio, 1.62. And by the way, the letter or Greek letter that represents the golden ratio most likely is the Greek letter phi. That's PHI. I won't worry about too much. It's just a Greek letter, just like alpha, beta, omega, or any of those. It's just used as a variable, just like pi is from the Greek alphabet. So anyway, this idea of this ratio, this 1.62, can be used in what the very basic ideas with a golden rectangle. And if you search on some ways that golden rectangles are used, one is if you look in the diagram, it can be demonstrated by the Parthenon in Greece, and the Parthenon can be thought of as being divided up into multiple different golden rectangles, or designed on basically a golden rectangle. There are places in our area, such as Daring Hall on Virginia Tech's campus, that uses a lot of golden rectangles. I kind of cut and paste the picture with some of the golden rectangles that can be found in the building. So the idea is that you design these rectangles where the ratio of the sides is about 1.6, 1.7, somewhere in that neighborhood. And as mentioned, a lot of schools that teach interior design, they will use the golden ratio in their designs, even in clothing, but could be also, if they're designing homes or buildings, or designing, specific things about a building, they often will use golden rectangles. So moving from the golden rectangle to the golden cross, the idea of the golden cross, again, is based on the golden ratio, but as you can see in the three formulas, the base, if you divide the cross into top, bottom, width, and height, what happens is if you divide the bottom portion by the top portion, you get the golden ratio. If you divide the overall height of the cross divided by the base, you get 1.62. And if you divide the height again by W, the width, it also is the golden ratio, pardon me. So you get three golden ratios within it. One of the shortcuts you will take is that if that's true, then the top portion will be equal to the width. T will equal W, and I will assume that in the next problem that I do. But that's just your standard measurements for a golden cross. And often most crosses you might see, whether it might be on a necklace someone's wearing, or outside a church, often those are based on a golden cross. So that's used frequently. Okay, so let's do an example where we find the missing value. So is the cross shown? Well, first we're going to do just to check to see if it's golden cross. My mistake, then we will find the missing value. So what we're going to do is to check to see if this is a golden cross. And notice that the top portion is 3 centimeters, the bottom portion is 4.87 centimeters, and the height is 7.86 centimeters. and W is 4.85 centimeters. So we're going to check all these measurements. So let's try this and see if it works. Again, I got the picture, same cross to the right. So let's take B divided by T. So if we go 4.86 divided by 3, you can do that on your calculator. It will come out to approximately 1.62. Now on your calculator, do H, which is the overall height of the cross is 7.86 divided by B, which is 4.86. Again, that comes out to approximately the golden ratio. And if you do H, which is 7.86 divided by 4.85, it also comes out to approximately about 1.62. So that's just a general check of doing height divided by bottom divided by top, height divided by bottom, and then height divided by W. All right, next one. This is the one where we have to find the missing values. So given the value of the top segment of the cross is 10 inches, we're going to find the values of H, B, and W. That will make the cross a golden cross. As you can see, we're going to round to the nearest hundredth. So here I got the cross again. So the first thing I'm going to do is basically go B divided by 10, because B divided by T is the golden ratio. So we'll go B divided by 10 is 1.62. That gives me a simple equation to solve, because if I'm dividing B by 10 and getting 1.62, I can simply solve it by timesing by 10. So if we multiply both sides by 10, we will get that the 10s cancel on the left, and you get B is 1.16.2 inches. So there's the first missing measurement. The next one is H. Well, recall all H is basically the top plus the bottom. So 10 plus 16.2 is 26.2. And let me fix that. I realized I had a typo. There we go. So H will be 26.2 inches. And then, of course, W will equal B. That's the quickest way to do it. And you get 16.2. And we're done. So in the PowerPoint, number 3 is a second example that you can try. I'm actually going to go ahead and move on to the golden box at this point. And then I'll talk a little bit about where the golden ratio occurs outside of architecture / kind of interior design type of questions. So the golden box is basically a box that's constructed of 4 golden rectangles. Now, it's impossible to construct a box that every face is a golden rectangle, but what you can do is make a golden box that 4 of the faces are golden rectangles. So what you can do to accomplish this is basically use the 2 formulas. W divided by H is the golden ratio, and L divided by W is the golden ratio, 1.62. So what we're going to do is do an example where I give you a missing value, and then you have to find the other sides of the golden box. So as you can see in this example 4, I have a golden box that has, I have a box with a height of 3 centimeters, but what I want to do is find W and L that will make the box a golden box. So taking one measure, can we find the missing values W and L? Let's try that. So first thing I'm going to do is use the first equation, which is W divided by H is the golden ratio, 1.62. Recall that H is 3, so W divided by 3 is 1.62. And what happens? Again, we can times both sides by 3. The 3's cancel on the left, and we get that W is 3 times 1.62 is 4.86 centimeters. That is side W. Now we can find L since we have W. So what we do is we go L divided by W is the golden ratio, 1.62. So L divided by the new W, which is 4.86, is 1.62. Timesing again by 1.62 times 4.86, we get that the new length of my golden box is 7.87. So there's kind of a rundown of how to do a golden box problem again. Again, find the missing side W, take that new value, and then plug in to this equation here. L divided by 4.86 is the golden ratio, and then timesing, you get the L. Okay, there is an example 5 that you can do, and another golden cross example that I left in the notes. I wanted to highlight how to do a golden cross and a golden box. I will mention some things about the golden ratio. One thing is, supposedly Leonardo da Vinci liked to use golden rectangles in his paintings. So as you can see, I took a self-portrait and showed you, basically you could construct a rectangle around his face. That's a golden rectangle. It's kind of a measurement. Your face would then be a little bit longer than it would be wide. But again, he based the face on a golden rectangle. You can also supposedly do this with the Mona Lisa. There may be an activity that you could find online that would show you how to put a golden box around the Mona Lisa face. Anyway, here's the other example. If you look at the diagram on the right, the box with the squares, notice that you have in the center, you start with a square that's 1 by 1, and then you add to that, you expand out another 1 by 1. That creates now a length of 2, so you can do a square that's 2 by 2. It's here. And then you can do 3 by 3, because 2 plus 1. And then that creates a new side. If you go 3 plus 2 is 5. Then you can go 5 by 5 and make a rectangle or a square. And then you can go 3 plus 5 is 8. And then do a rectangle that's a square that's 8 by 8. And as you can see, I drew the swirl in there that is similar to what they call the Nautilus shell. So one of the ideas is you can use this ratio 1, 1, 2, 3, 5, 8 and continuing. And that ratio produces what is called a Nautilus shell. Now, the thing that's interesting about that ratio, 1, 1, 2, 3, 5, 8, and if I continue adding consecutive numbers, I would get 13, 21, and then 34. That is known as the Fibonacci numbers. And so that sequence of numbers, the Fibonacci numbers, is connected to the golden spiral. But anyway, it's 1, 1, 2, 3, 5, 8, 13, 21, 34. One thing you can do with these numbers is starting with 3, 2, and 3. If you divide 3 by 2, that comes out to 1.5. And then if you divide 5 by 3, that comes out to 1.6. And you can keep doing that, and it gets closer and closer to the golden ratio. You can do 8 divided by 5 is 1.6 as well. But then when you do 13 divided by 8, it's 1.625. We're getting closer and closer to the golden ratio. And then if you do 34 divided by 21, this on your calculator, that's about 1.62. So all those numbers, if you divide consecutive pairs of numbers, you get the golden ratio. So there is a connection to that. Just going through and, starting at 1 and 2, just do 2 divided by 1, 3 divided by 2, 5 divided by 3, 8 divided by 5, 13 divided by 8, 21 divided by 13, 34 divided by 21. Just doing that pattern where you divide the one number by the number before it, it will produce, eventually starts to produce numbers that are very close to the golden ratio. Another thing, if you were curious, and then I'll close the lesson out, there is an artist that uses the Fibonacci numbers in his music. And the piece of music is as you can see, it's Bela Bartok Music for Strings, Percussion, and Celesta. If you wanted to Google that and listen to it, listen for piano keystrokes, very high-pitched piano, probably all the way on the left on the piano keyboard, but he basically strokes out the Fibonacci numbers throughout that piece of music. If you listen carefully, you can hear it. I don't know if I can get this link to work, and I don't think it would show up anyway. I think that link, unfortunately, has gone bad, but you could certainly search on Google and find, I'm sure you could find the music online somewhere. That's kind of hard not to find, find music that's not on the internet. Usually you can, if you search enough, you'll find it on YouTube or some other site. Okay, so I kind of rambled a little bit there, but don't worry so much in terms of this next test. The thing that you have to know for the next test is be able to do a golden cross, be able to do a golden box problem. If you can do those two types of problems, that's the main thing that you will have to do on this next test coming up. All right, so that's it for the golden ratio. The next unit will be on fractals. Until then, till I post my next video, that's it. So thanks for listening.